All right. Sorry about it, folks. So it's my great pleasure to welcome you to FOTC Summer School and workshop on sublinear algorithms. Today and tomorrow, as you know, we'll have a summer school, and the workshop will start on Wednesday. Do we have any announcements before we start? Yes, we don't. So let me just say it's a great pleasure to see you guys. You know, it's the first event we are organizing since the COVID. So you know, it's really great to see you all in person, right? And we booked a large room. So if you want to isolate yourself, there is plenty of room. Good. So without further ado, it's my great pleasure to introduce Jalali Nelson. Jelani is a professor at UC Berkeley. You know, he has made many exciting contributions to the area of dimensional reduction, streaming algorithms, sketching algorithms, and many others. And today he will give us a sequence of 2 lectures with a break in the middle about dimensionality reduction. Take it away, Jelani.
Test. 1, 2, 3. Testing, 1, 2, 3, testing. Testing, testing. I'm going to keep talking. Test 1, 2, 3. Oh, you can hear me without the mic? Okay, I'm going to keep talking and okay, so it looks like if I do this, it catches it, but if I do this, it's not catching it. Is that right? Yes? Okay. Great. Okay. Well, I'll try to keep my chin down. I don't know. It's kind of awkward because like I'm not looking at you. But yeah, so if you lower the dimension, there are some obvious benefits. Like presumably, whatever algorithm you're running, the runtime depends on the dimensionality of the data. So if you can reduce that, then your algorithm probably runs faster. Another one is like distributed applications. Again, maybe the communication between compute nodes depends on the dimensionality. So if you can reduce that, then maybe you're using less bandwidth. We're going to see some of these kinds of applications. But of course, you want to reduce dimensionality in such a way that you don't disrupt whatever you're trying to compute, right? So obviously, I can just say, okay, well, the dimensionality is 1. Everyone gets mapped to a point on the line, but then it doesn't. It disrupts whatever it is that I'm trying to do, clustering or whatever. So I need to do dimensionality in such a way that I preserve some geometric structure of the data. But ideally, I want to make the dimension as low as possible while preserving whatever I want to preserve. Okay, and this is a very popular method. So the random projection method is one method for dimensionality reduction, which you're going to see today. So in particular, it's what I wrote there. You pick some random matrix, pi, and x gets mapped to pi x. And you do this again as a pre-processing step. So there are other dimensionality reduction methods that you may have heard of, like PCA, low-rank approximation, and kernel PCA, and isomap, et cetera, et cetera. In this talk, I'm not really going to talk about most of these, although for some of these, like PCA, so I guess what I'll say is, for these, like say PCA, the idea is that even though your data is high dimensional, it really has a low dimensional structure, right? And you're trying to find that low dimensional structure. Whereas that's not the goal of what I said in the previous two slides. Previous two slides, I'm not going to assume that there's low dimensional structure. It could be actually really high dimensional data, but I still want to somehow map to low dimension as an algorithmic tool to like speed up algorithms, right? Which is different from the goal here. The goal here is not, PCA is not necessarily an algorithmic tool. It's more about understanding your data. But as we will see, or we won't see too much, but it turns out that you can use the algorithmic tools for dimensionality reduction to do some of these things even faster. So you can do faster approximate PCA by using the random projection method, for example. So they're like orthogonal, I would say. Yeah, so as I say, orthogonal to and complements, they're not necessarily in opposition. Okay, so a cornerstone result in this area is something known as the Johnson-Lindenstrauss lemma, and you're going to see that a lot in this talk. Just out of curiosity, show of hands, who here has heard of the Johnson-Lindenstrauss lemma? Okay. Actually, maybe just so I know my audience, who here is a student? Okay, undergrad student. Grad student. Postdoc. Or beyond. Working as a full-time person somewhere. Okay. Okay, great. So it seems like it's grad student heavy. So what does the Johnson-Lindenstrauss lemma say? It says that if you have a point set capital X of size n, it doesn't matter what dimension, and this is a subset of L2, it doesn't matter what the dimensionality of the original point set is. There's always an embedding from that point set into m-dimensional Euclidean space, such that where m is this bound, 1 over epsilon squared log n, with distortion 1 plus epsilon. So what does distortion 1 plus epsilon mean? It means that the distances are preserved up to a 1 plus epsilon factor. So if you look at any points, little x and little y are in that point set. If you look at the distance between f of x and f of y, which is the embedded version of the points, those distances are approximately what they used to be. And maybe another show of hands. Who here knows how to prove the Johnson-Lindenstrauss lemma? Okay, so that's a smaller number of hands. Okay, so for any vector, so what this says is for any vectors in arbitrary dimension, you can always map to O of log n dimensions while approximately preserving distances. How do you usually prove the Jl lemma? You prove first what's called the distributional Jl lemma, which says that for any epsilon and delta, which are less than a half, there's a distribution d epsilon delta over matrices, m by d matrices, where m is this bound, 1 over epsilon squared log 1 over delta. So in particular, it doesn't depend on the dimension d. Such that for any vector z in d-dimensional space, with high probability, pi z will have norm almost the same as z, right? So pi z will have norm between 1 minus epsilon times the norm of z and 1 plus epsilon the norm of z. And the probability that it doesn't, that it fails to preserve the norm up to this 1 plus epsilon factor is at most delta. So with high probability, it does. And then once you have this DJL lemma, we're going to see how to prove it. But once you prove this lemma, it's pretty short to then use it to prove the JL lemma. And you just prove it using a union bound. So you set delta to be 1 over n squared, where n is the number of points in JL that you're trying to preserve. And then now for any fixed little x and little y in the point set, you consider z being the difference vector of x and y, x minus y. And then what this says is that pi times the difference vector has almost the same norm as the difference vector. So pi x minus pi y has almost the same norm as x minus y with high probability. Okay, that's exactly what you want. And then you union bound over all the pairs to say that all of them are preserved simultaneously. And the number of pairs is n choose 2, right? So you'll say you're setting delta to be less than 1 over n choose 2. So set delta to be 1 over n squared. And then what's the dimension? The dimension is 1 over epsilon squared log 1 over delta, which is 1 over epsilon squared log n, right? So that's where the 1 over epsilon squared log n comes from. And the embedding is just x gets mapped to pi x. Okay. And the reason it's called the random projection method is because the very first proof of the distributional Jl lemma, well, what do you have to do? You have to specify what is d epsilon delta, right, in the proof, and then prove that this d epsilon delta works. So the very first proof by Johnson and Lindenstrauss in the 80s, d epsilon delta was pick a random subspace of dimension m and then just do orthogonal projection onto that subspace with some constant scaling to get the correct expectation. So it's called the random projection method. It's not the only d epsilon delta that works. It's just the first one that people looked at and analyzed. So in this talk, I'm going to try to cover as many of these bullets as I can in 2 hours. We'll see how far we get. But there's some natural questions like, okay, this is all Euclidean norm. What about doing dimensionality reduction in other norms which are not Euclidean? How do you prove the distributional Jl lemma that I just showed you, right? This d epsilon delta, how do you show that it works? How about these m's? So I said in DJL, in distributional JL, I said that the m you get is 1 over epsilon squared log 1 over delta. Can you do better? Can you get a lower dimension? And how about for JL? Can you get a lower dimension for JL than 1 over epsilon squared log n? Another question that I think is a natural question is algorithmic speed, right? So the whole motivation I gave you for why we want to do dimensionality reduction is to speed up algorithms, right? So now you have a pre-processing step where you're doing the dimensionality reduction, and then you're running your algorithm on the low dimensional data. So obviously, the lower the dimension you get, the faster the second part. But you got to also consider how fast is the first part, or slow. How slow is the first part? The part where you actually do the dimensionality reduction. So we want to construct distributions or matrices pi that do our JL for us that are algorithmically friendly, where you can map x to pi x very quickly. Another one is de-randomization. So pi is going to be a random matrix. It's going to be a big random matrix. Think of D as large, like you have some very high dimensional data. So it's m times D entries in this matrix. Is there some more randomness efficient way of coming up with pi such that you can store it using many fewer random bits than MD? Okay. Okay, and then there are some problems where you can solve the problem like in a black box way using JL. Like, oh, this problem is all about calculating some distances. Obviously, if I preserve the distances, then it'll preserve the answer to the problem. Okay, and then you'll get some, therefore, if I map the dimension 1 over epsilon squared log n as JL says, then I'll preserve the answer to my problem. But if you have some particular problem like k-means clustering or nearest neighbor search or whatever, maybe you don't need to go through JL. Maybe there's a way to directly analyze dimensionality reduction for your problem for clustering and argue that you can get even less dimension for that particular application. So we'll see a little bit of that. Also instance-wise bounds, meaning yes, 1 over epsilon squared log n is the best you can do in general, but for my data set that I have right here, maybe I can do better. So we'll see a little bit of that. And then the last thing I'll mention is generalizing JL, going beyond JL and doing more. So there's something called terminal embeddings, which is a recently explored thing, which is somehow more powerful than JL. So we'll see if we get there. So let's start with the first one. What about other non-Euclidean norms? So the punchline is that if you have a lemma like the Jl, so if you have a norm space and you have a statement that's like the Jl lemma, then your norm space has to be almost Euclidean space. In other, like the informal statement of this theorem is basically Euclidean space is the only norm space where JL holds, or something like JL holds. Okay, what's the formal statement? The formal statement is, suppose Z is a norm space. Think of Z as like infinite dimensional. Okay. So suppose Z is a norm space that has the following property. For any endpoints in Z, there's a linear subspace of dimension O of log n such that I can map to that linear subspace with a linear map with constant distortion. So for example, Z might be Euclidean space. And this is, and the linear subspace is just like the first few dimensions, okay, of this infinite dimensional Euclidean space. So JL tells you that this is true, right? JL tells you that if Z is Euclidean space, this is true. But let Z be another norm space where this is also true. Then if your space satisfies this property, if Z satisfies this property, every finite dimensional subspace of Z embeds into Euclidean space with distortion 2 to the 2. So if it's a k-dimensional subspace of Z, it embeds into Euclidean space with distortion 2 to the 2 to the log star k. Just show of hands, who knows what log star means? Okay, or who doesn't know what log star means? So log star is just the number of times you have to take iterated logarithm before you get down to 1. So for example, if you look at 2 to the 2 to the 2, log star of that is 3. You have to take log base 2 of it 3 times before you get 1. Or 2 to the 2 to the 2 to the 2, the log star of that is 4. And this number grows, 2 to the 2 to the, like a tower of 2s of some height grows very, very fast, right? So I guess 2 to the 2 is 4, 2 to that is 16, 2 to that is 65,000 roughly, 336. 2 to that is extremely large. It's like way bigger than the number of particles in the universe squared, or even more than squared. Okay, so in the physical universe, you'll never need to take log star of anything to get, log star of anything you take in the real world will always be less than 5, or at most 5. Okay. So think of log star as a really, 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 really slowly growing function. So what this says is that every k-dimensional subspace of your norm space embeds into Euclidean space with very, very, very low distortion. So it's like almost Euclidean, right? So that's why I said the informal theorem, right? That any norm that satisfies a Jl type theorem must be almost Euclidean. So this is the formal version. There's also a lower bound showing that, you could ask the question of this 2 to the 2 to the log star, like, can you replace it with a constant, for example? Like maybe it actually embeds, maybe there's a better version of this theorem that says it actually embeds into Euclidean space with constant distortion. That's not true. You can construct counterexamples where the distortion is actually 2 to the inverse Ackermann of k, which is another really slowly growing function. But okay, so that's all I want to say about the first bullet. I'm not going to spend too much time on the first bullet. Let's move into how do you prove the distributional Jl Lemma? Okay, so remember, this is what the distributional Jl Lemma says, that for any epsilon and delta, there's a distribution over linear maps embedding into very low dimension, such that for any fixed vector, a random linear map from your distribution preserves it with high probability. Okay. So first, I'm going to, on one slide, I'm going to sketch a short proof of distributional JL. I'm not going to fill in all the details, but I'll tell you like the skeleton of how the proof goes. And then after that, I'll show you a different proof, which is not as short, but it has the advantage that it's a more extendable or flexible proof. Like you can use that, you can modify that proof to prove other things too. Okay. So first of all, some notation. For random variable x, if I look at the expectation of e to the lambda x, I guess that's the moment generating function. So I'm going to define the psi function as being ln of something like the moment generating function around the mean. Okay. And there's a definition, which is that I'll say that a random variable is subgamma if, okay, so have people heard the term sub-Gaussian? Anyone know what sub-Gaussian means, right? So sub-Gaussian basically means that a random variable decays at least as fast as a Gaussian, right? So a Gaussian decays at a rate e to the minus lambda squared. A sub-Gaussian decays at least as fast as that. Okay, so subgamma is something similar. There are two parameters. So sigma in a sub-Gaussian random variable, sigma would be like the standard deviation. So in a subgamma random variable, sigma is still like the standard deviation, and b is like, it's a mix between sub-Gaussian and exponential and sub-exponential. So b is like the exponential parameter. So we say a random variable is subgamma if it has kind of a sub-Gaussian-like behavior in its moment generating function, but only up to lambda, up to a certain threshold, only when lambda goes up to 1/b, right? Then this psi function is at most some specific thing, lambda squared, sigma squared over 2, whatever, okay? Okay, so that's the definition of subgamma. And there are some properties of subgamma random variables that are not that hard to prove, but I'm not going to do them here today. The first one just says that if you have a bunch of independent subgamma random variables, their sum is also subgamma, and the parameters of the sum depend on the parameters of the summands. In particular, the variance becomes the sum of the variances, and the exponential parameter becomes the minimum of all the exponential parameters. And the second bullet is that if you have a random variable that's subgamma, you can prove a tail bound. Actually, I really should have said around the mean. So it's really the probability that x deviates from its mean by more than t. The probability that happens is at most a mix of a Gaussian tail and an exponential tail. So e to the minus t squared over 2 sigma squared is like how a Gaussian decays, and e to the minus t over 2b is like how an exponential decays. So you get the sum of the two, which is like the max of the two. Okay, so suppose now that we take our d epsilon delta distribution over matrices to be such that the entries are independent, and they're each 1 over square root m times a sub-Gaussian random variable, like a Gaussian, with mean 0 and variance 1. So what are some examples of sub-Gaussian random variables? A Gaussian is sub-Gaussian, or like a plus minus 1 random variable, a Rademacher is sub-Gaussian. So any of those would work. Okay. So that's how we're going to choose our matrix. It's going to be a dense random matrix with independent sub-Gaussian entries. Then if you look at it, so remember now, we care about preserving pi times z, right? Z is our vector. We want to preserve pi times z. So what is the rth entry of pi times z? The rth entry of pi times z is yr. It's the dot product of the rth row of pi with, sorry, that x should be a z, with the vector z. And since all the entries in pi are sub-Gaussian, this sum is sub-Gaussian. Okay, I didn't define sub-Gaussian on the slide, my apologies, but that's some other jargon, okay? So since you're summing up a bunch of sub-Gaussian things, yr is sub-Gaussian. But what you care about actually is not yr, you care about the norm squared of pi z, right? So it's like the sum over r of yr squared. So yr is sub-Gaussian, and there's a lemma that if you have a sub-Gaussian and you square it, it's now subgamma. So yr squared is subgamma. So the sum of yr squareds is also subgamma by the first bullet, because when you sum up subgamma things, you get a subgamma thing. And then the second bullet says that sum now satisfies a Bernstein type inequality, so you get a tail bound. Okay, so without me going through all the precise calculations, this is like how the sketch of the outline of how you could prove DJL using knowledge of subgamma random variables. I'm going to do a longer, less simple proof, as I mentioned, because it extends to other settings. And the strategy outline is we're going to first show three inequalities in succession, and then we're going to use the last one to actually prove DJL. So just show of hands, who's heard of any of these three on the slide? Okay. Okay. So at the end of the day, we're only proving the first two because we want the last one. At the end of the day, we really want the Hansen-Wright inequality because that's just going to imply DJL for us. What is Hansen-Wright inequality? It's a concentration bound. It's a tail bound for quadratic forms. So think like you have a matrix A, and then you have, let's say, a sub-Gaussian vector G, and you have the sum over ij of gi, gj, aij. And you want to understand, like, this quadratic form, what's its concentration around its mean. So that's what the Hansen-Wright inequality gives you. And why is that the thing? Why is that helpful for us? Okay, so remember, if we choose the entries of pi to be independent sub-Gaussian random variables, then, okay, the thing we care about is pi z, the norm of pi z. But I claim that pi z is equal to some matrix times G, where when I say G, I'm saying take the rows of pi and just concatenated them into one really long vector that's an MD dimensional vector. Okay? So, I mean, the entries of pi z are like the first row of pi dotted with z, the second row of pi dotted with z, the third row of pi dotted with z. Okay, so let's just define a matrix BZ, which just has z transpose going kind of down the matrix. It's an MD by MD matrix. So in the very first row, it just has z transpose taking up the first d entries. And then the next row, there's d zeros followed by z transpose again. And the next row, there's two d zeros followed by z transpose again. And now the point is, if you take this matrix times G, what's the first entry? The first entry is z dotted with the first row of pi. So I basically just, yeah, so they're the same. Pi z and bzg are the same. They're equal. They're equal vectors. And then now what I care about is pi z L2 norm squared, which is the same thing as bzg L2 norm squared, which is, a vector norm squared is just it transpose times itself. So that's g transpose bz bzg. It's a quadratic form, right? So this middle matrix, B transpose B, is some matrix A. So this is G transpose AG. And I want to understand how concentrated is this quadratic form around its mean, right? So that's why it's useful to have a concentration inequality for quadratic forms. So that's our goal now, is to prove the Hansen-Wright inequality and then use it. Any questions about anything? Yeah. Oh, so yeah, so let's see. So right there, the entries of pi are just independent sub-Gaussians or whatever. Let's say sub-Gaussians, and then scaled by root m, right? So this is, so my G vector is just like, yeah, maybe I'll just write it. I know the people on Zoom can't see, but so let's say pi is like a matrix, and it's like G11, G12, and then G21, G22. And then like G, I'm defining G as just being this like MD dimensional vector that just has, you know, like the first row of pi is there, and then the second row of pi is there. So that's G, that's the G vector. I stack the rows of pi on top of each other. Any other questions? Okay. So first, let's prove, we're working toward proving this concentration bound for quadratic forms. So just recall some notation. If you have a random variable, you can define the p norm of the random variable to be the expectation of x to the p to the 1 over p. And this is a norm. It satisfies like everything a norm does, triangle inequality, et cetera. Then if sigma is a vector of IAD plus minus 1s, then we have that the p norm of sigma dot x is at most root p times the L2 norm of x. That's Khinchin's inequality. There are many ways to prove it. Here's one way to prove it. The way I'm going to prove it is by comparing to a Gaussian. Okay, so the G's are actually ID Gaussians, mean 0 variance 1. And then I'll just walk through this step by step. This is the thing we're actually trying to bound, right? This is sigma dot x. This is sigma dot x right here. And I'm just going to multiply by 1 in a fancy way. So notice that I put the expectation over G inside the norm. So what is the expectation over G of the absolute value of GI? It's a number, right? What is the expected value of this thing? It's a number. It happens to be square root 2 over pi. It doesn't really matter what it is, but it's a number. So since that number is square root 2 over pi, I multiply by square root pi over 2 on the outside to cancel it. So all I did was multiply by 1. And then I can take this expectation over G and pull it out the norm by Jensen's inequality. So now this LP norm is an expectation over two things. It's an expectation over sigma and over G. And what's a random sign times the absolute value of a Gaussian? It's a Gaussian. I can decompose a Gaussian into its magnitude times its sign. And then now if I take G dot a vector, if you take so what is GI times XI? GI is a Gaussian. GI times XI is also a Gaussian, just with a different variance. Its variance is now XI squared. So I'm summing up a bunch of Gaussians where the ith Gaussian has variance XI squared, and they're independent. What happens when you sum up a bunch of independent Gaussians? You get a Gaussian, and the variances add. So now this sum is itself just a Gaussian, whose variance is the sum of the XI squareds, which is a number. So I can pull that number out, and then I just have the p norm of a Gaussian, and you can, that's just a closed form, that's something, whatever it is. The p norm of a Gaussian is basically root p. Right? So that's one proof of Khinchin's inequality. I'm sorry?
On some of the previous slides, you had something like this inequality is tail-bound for linear quantity.
Oh, yeah, okay, right. So I said tail-bound, but I proved a moment-bound. Is that your question?
Yeah, maybe sort of.
Like I said, it's a tail-bound. So, I mean, this is a linear form, right? It has mean 0. So, so the deviation from its mean is the deviation from 0. So what's the probability? What's the probability that this sum is bigger than t? So I guess, yeah. One thing to know, and I'll write this down here, is basically tail bounds and moment bounds are basically the same thing, because notice that the probability that some sigma I, let me just call this Z. The probability that capital Z is bigger than T. Okay, so capital Z is the sum of sigma I xi, is, right, equal to the probability that Z to the P is bigger than T to the P, which is at most the expectation of Z to the P over T to the P by Markov's inequality. Right, and this is exactly like the P norm to the Pth power. Does that answer your question? It's like if you can bound. It's a linear form where they're sub-Gaussian, right? Where like, it's like, yeah, so Khinchin's inequality is, yeah. But I mean, okay, so yes, it's a very specific choice of what the random variables are. They're plus minus ones in this case. But also for us, at the end of the day, we're just trying to prove DJL. And like for DJL, we get to choose d epsilon delta. So I'm just going to choose d epsilon delta to have plus minus 1 entries. Yeah, so it's enough for me. So now we have a linear form that works for plus minus 1 random variables, where you dot it with an arbitrary vector x. Okay. Okay. So is that okay? Okay. Okay, so that's a tail down for linear forms. And then now we're going to need another thing, which is decoupling. So decoupling says now, suppose you have two different Rademacher vectors, sigma and sigma prime. They're independent of each other and they're both uniform. And let's say you have a matrix capital A whose entries are Aij. So Aij are the entries of a real matrix. Then if what you want is the P norm of this random variable, it's bounded up to a constant. This less than twiddle just means like less than a constant times the right-hand side. So it's bounded by a constant times the right-hand side. So the difference is this is sigma I, sigma j. This is sigma I, sigma j prime. I also put the diagonals back in, but that's less important. Okay? So that's the statement. No, this is just the bounding the norm, bounding the P norm. Yeah.
But when you use the sign in general, this is always like an absolute.
This sign means big O. Less than twiddle just means big O. The left-hand side is bounded by a constant times the right-hand side. Okay, so here's the proof, or here's a proof. Let eta i's be independent Bernoulli with mean a half. So it's just a coin flip, 0 with probability 1 a half, and 1 with probability 1/2. Okay, then I claim there exists a particular, a particular 0, 1 vector eta star, such that the following is true, and I'll just walk through this. So this is the thing that we had originally on the left-hand side. And here what I did is the same exact trick where I just multiplied by 1 in a weird way. So inside of the norm, I added expectation over eta of eta I times 1 minus eta j, and then what I had before. So what is expectation of eta I times 1 minus eta j? Well, it's a half times a half, which is a quarter. So I just multiplied by 4. So I didn't do anything. I just multiplied by 1. But then now again, I can use Jensen's inequality and take this expectation over eta outside of the norm. And now the randomness, the expectation is over two things. Sigma is random and eta is also random. And just remember what P norm means. P norm means expectation of that thing to the Pth power to the 1 over P. So I can think of that as like the average over eta, the average over sigma of something. Let's think of it as the average over eta of blah. Okay? This whole thing for me is blah. The average over, the expectation over eta of blah. Now, there must be, not everyone can be below average, right? There must be an eta that achieves at least the average. I'm just going to call that eta star. So eta star is now a deterministic. It's a fixed 0, 1 vector. There must be an eta star that achieves at least the average. So I can just eliminate this expectation over eta and put in eta star. Okay, so now there's no more random, only sigma is random now. Okay. And now what I'm going to say is, for that fixed eta star, define a subset S of the coordinates, which is all the I such that eta I star is 1. Okay, and now let's write what we had at the end last time. This whole sum is the same thing as the sum I in S, sum J not in S, or J in S bar, of Aij sigma I sigma j. Okay, and now since the inner sum is on a disjoint set from the outer sum, I can simply replace all the sigma j's by sigma prime j's, and it's exactly the same distribution. And then now notice that this randomness only cares about sigma projected to S and sigma prime projected to S bar. Sigma, the elements of sigma which are in S bar don't matter. They don't appear in the sum. And similarly, the elements of sigma prime in S don't matter because they don't appear in the sum. Okay. So now the people who are missing from the sum, let me put them back. And I'm going to put them back inside the sum. So inside the sum, I'm going to take the expectation over sigma S bar and the expectation over sigma prime S and put everyone back. And everyone who I added back now is contributing 0, right? Because expectation over sigma I of sigma I is 0. So this is the same trick where I'm just like adding in 0 in a funny looking way. But now I can do Jensen again and pull out these expectations outside the norm. And now the norm is over everything. It's over all of sigma and over all of sigma prime. So, and that's exactly what I wanted. I have the sum of Aij, sigma I, sigma j prime. Okay, so that's it. That's the proof of the decoupling lemma. And now let's use these to prove the thing we actually cared about, which is a moment bound for quadratic forms. So the Hansen-Rod inequality says, if you have a random plus minus 1 vector and a fixed matrix, and you look at this quadratic form, sigma transpose A sigma, and you look at its deviation from its mean, these central moments are bounded. So the P norm is bounded by root P times the Frobenius norm plus P times the operator norm. So operator, for us, A is going to be a real symmetric matrix. So operator norm is just the magnitude of the largest eigenvalue. Frobenius norm of a matrix, if you don't remember, is you take the sum over ij, aij squared, and you take the square root. So it's basically you treat your matrix as a big vector and take its Euclidean norm. Okay, so how do you prove this? And I promise you, I think once we're done with this slide, it's going to be less like following equations in this talk. Okay, it's going to be a little more exciting, maybe. I hope. I know this can get very boring and tiring. So the first step is, so again, because we subtracted off the mean basically is the diagonal. I mean, the mean is the diagonal terms because you have sigma I squared, which is always 1. So you have aii. Basically, this is just the trace of the matrix A, which are the diagonal terms. So you're killing all the diagonal terms from this quadratic form, which is exactly what decoupling had. It's like you got rid of the diagonal. So you can apply decoupling and say that this is bounded by sigma transpose A sigma prime, where sigma prime is now a different vector. Okay. And then now you can use Khinchin's inequality because this is now a linear form, right? If you fix sigma prime, then what you have is like sigma dotted with A sigma prime. So like this is my vector X, right? That I use, so it's like a linear form. Once I condition on sigma prime, it's a linear form. So I can apply Khinchin's inequality. And what I get is root P times the norm of A sigma prime. But A sigma prime is a random vector. Oh, everything okay, Piotr? Oh.
Sorry, I was just trying to inconspicuous.
Oh, yeah. Sorry, I guess I ruined that. So what matters is the L2 norm of A sigma prime, the L2 norm of X. But A sigma prime is a random vector, so I mean, it still lives under this P norm that was there. And then now, this thing, maybe this is, if you're not used to seeing this, maybe this is a little weird looking, but let me just write something for that. So, right, if you have the p norm of z, this is equal to the expectation of z to the p to the 1 over p. Like that's the definition, right? And then I can just say, well, this is the same thing as expectation of z squared to the p over 2 to the 2 over p square root. Okay. I mean, I'm just like playing funny games, but it's the same thing. So that's all I did over there. I just said, well, the p norm is equal to the p over 2 norm square root, but where you square the thing that was on the inside. Okay. And actually, good. And then now what I can do is I can do triangle inequality to basically add in and subtract out the expectation of a sigma prime L2 norm squared. And actually, okay, maybe technically I should have done the triangle inequality before I did that step, but it would give you what I wanted. So this thing here is a number now, and it turns out this number is the Frobenius norm squared. And then this is some other quadratic form deviating from its mean. So this is the Frobenius norm squared, and there's a square root. I can pull it out and say root p times the Frobenius norm. And then this root p multiplies that, but this root p also multiplies that. So I have root p times this. Okay. So I guess the thing to note now in the very last line is I started off wanting to bound the p norm of a quadratic form, and I reduced it to wanting to bound the p over 2 norm of a different quadratic form. So I guess, what does that, I guess, make you think of? If you were to finish the proof yourself. Recursion, which in terms of proofs is induction, right? So basically just induct on p. So if you write p to be 2 to the k, you can just do induction on k. And if p is not a power of 2, let's say you're trying to bound the q norm, which is not a power of 2, well, if q is less than p, then the q norm is at most the p norm. So just round up q to the nearest power of 2, apply this to that, and then bound your q norm by that. So you can get it for all p. Okay, so that's how you prove, that's one way of proving the Hansen-Wright inequality, is using decoupling with Khinchin and an inductive argument. Okay, now, once you have, and I guess this goes back to the first question you asked me about, like, why is this a tail bound for linear forms, right? Once you have moment bounds, the moment bounds imply tail bounds because you can apply Markov on a high moment. So the fact that we bounded the p norm of this thing by something is equivalent to saying that we have a tail bound for this quadratic form around its mean. And what you get by applying Markov to a high moment is a mix of a Gaussian tail and an exponential tail. Okay. And remember now, the thing we cared about was a quadratic form. We said that pi z L2 norm squared was a quadratic form. So I can say pi z L2 norm squared is that quadratic form. Let me just define AZ to be that middle matrix B transpose B. And now, because of what B was, A is just a block diagonal matrix with m blocks, where each block is equal to ZZ transpose. Okay, if you remember, B was this matrix that had Z transpose, Z transpose, Z transpose. So if you take B transpose B, you end up getting ZZ transpose over and over again as a block diagonal matrix. You can calculate what its Frobenius norm is, you can calculate what its operator norm is, and then you apply Hansen-Wright and you're done. Okay, Hansen-Wright just gives you exactly what you want. So finally, okay, I consumed maybe a little too long on that, but this is another way to prove DJL via the Hansen-Wright inequality. Okay. So I want to move on to other things, but before I do that, any questions about the proof of DJL? So now let's start answering questions about optimality. Can you do better for DJL? So DJL, remember the target dimension we got was this, 1 over epsilon squared log 1 over delta. Can you do better than that? And even if you can't do better than that, that doesn't mean that you can't do better for JL, because, I mean, yes, you can use DJL to get JL, but maybe there's another way to get JL without going through DJL that's even better. So this next question we'll answer after that is, can you do better for JL? But first, let's start with, can you do better for DJL? So this is DJL. And there's a theorem. It was 2 different proofs that one goes through communication complexity and one goes through Yau's minimax principle. That they both say that for distributional JL, the M that you see there, that you see right here, is basically optimal. So it's only optimal up to a certain point, because obviously there's always another distribution that always works, which is the distribution that always spits out the identity matrix. Right? If d epsilon delta gives you the identity matrix with probability 1, that also preserves the norm of any vector. But it doesn't do dimensionality reduction, okay? But you know, that if epsilon is super small or if delta is super small, right? If this quantity is like such that it's bigger than d, then obviously that's not optimal. You would not want to do this. You would just want to use the identity matrix. So that's what the lower bound says. It says basically that bound is optimal up until the identity matrix kicks in, and then the identity matrix is optimal. So let me show you a proof that we had of why DJL is optimal. I'm not going to do a line-by-line calculation. I'll just show you the structure of the proof. Who's heard of Yau's minimax principle, just out of curiosity? Okay. Actually, I also want to know other things about the audience. So it seems that many of you are grad students. Who here is a grad student focused on theoretical CS? Okay, who here does something, a grad student not in theory CS, in another area? So it's just a few of you. So what are your areas? I'm curious. Telecommunications and security. Same. Oh, okay. Was there someone else who said they're not in theory, TCS? RL theory? Okay. Okay. So we're going to do a proof via Yau's minimax principle. For those who haven't heard it, I guess you'll now see it in action. So what does it say? So not what does Yau say, but what does the proof structure say? So this is what we know, right? You told me that d epsilon delta satisfies DJL. And what I'm going to prove to you is if d epsilon delta satisfies DJL, the target dimension, the number of rows of your matrices must be large. That's what I need to prove. So what does it mean that it satisfies DJL? For all z that have unit norm, so this is the sphere, for all z on the sphere, the probability that pi fails to preserve the norm by 1 plus epsilon is at most delta. That's what DJL means. Okay. Well, if that's true for all z, if it preserves the norm for all z, it must also preserve the norm of a random z. So let me now take the probability over z drawn from some distribution of the same thing. That still must be preserved with high probability. What is this distribution capital F? It can be anything I want. I'm allowed to choose it. It's true no matter what capital F is. Okay? And then now let me swap the order of the probabilities. So instead of taking z randomly at first and then taking pi randomly, I'll first choose pi, then choose z. It's the same random experiment. I just chose the order differently. And now again, okay, so the probability over pi, so for a random pi, the failure probability is at most delta, which must mean that there exists a pi in the support of this distribution. There exists a pi where that probability is at most delta. Not every pi can be, is this above or below? Let's see. Yeah, not every pi can be above average, I guess, in terms of its failure probability. And then you just prove that, this can't happen if F is chosen in a smart way. Like, if F is chosen in a smart way, there does not exist a matrix pi that can preserve a random norm from a vector in that distribution. And this is basically, this kind of argument is what's called the easy direction of Yau's minimax principle. And then you show that if F is chosen to be a certain hard distribution, which turns out to just be the uniform distribution on the sphere. So if F is just the uniform distribution on the sphere, and if M is less than d over 2, M is the number of rows of pi, then you can prove that for any fixed pi, it fails to preserve the norm of z with a certain probability. Therefore, since you need this probability to be less than delta, m must have been large. Okay. So this is a calculation. The fact that no pi can preserve norms with probability better than 1 minus that. That's a calculation. But once you do that calculation, you get the lower bound on m. Okay, so that's that. And I think I'm going to do this last one, optimal target dimension m. Oh, actually, we started, what time did we start? Like 10:05?
Yeah, like 10:05-ish.
Oh, 5-ish. Okay, so I think probably what's going to happen is right after we finish this next bullet, we'll do our 10-minute break, and then we'll come back. Okay, so now can you do better for JL? So this is a question that people have asked since the beginning. I mean, since the beginning of JL. So from JL's 1984 paper itself. And J and L themselves had an argument in their paper that said, for JL, you cannot do better than log n target dimension. The thing about which is the right dependence on n. The problem is that their argument was not sensitive to epsilon. So even if you drove epsilon towards 0, it would not change their lower bound. Their lower bound would just be some constant times log n, some constant independent of epsilon times log n. And then the first lower bound that actually managed to involve epsilon was by Noga alone in 2003, which the technique was using a tensor trick. I'm not gonna show you his proof because you'll see that there's a better lower bound. And then finally the correct lower bound came, which was 1 over epsilon squared log n. But that lower bound only worked against linear maps, where you insist that the embedding be, f of x is pi times x for some matrix pi. And then you show that if you insist on a linear embedding, then you can, there exist point sets where you cannot beat JL, where you actually need 1 over epsilon squared log n rows in your matrix. And I mean, in reality, all the upper bounds we have, all the proofs of JL we have are linear maps. So this showed that at least using the broad techniques we have that involve linear maps, you can't hope to ever do any better. But it still raised the question of, or left the question of, well, can you possibly do better with the nonlinear embeddings? Okay. And what you're going to see today is no, that actually we have an even now stronger lower bound that says, even if you allow yourself to use nonlinear embeddings, there exist point sets where you simply, mathematically, the embedding just doesn't exist. There is no embedding that does better than 1 over epsilon squared log n dimensions. So this is our theorem. It says, for any dimension d and for any number of points n, and as long as epsilon is not too small, there exists a hard set of points. Okay, capital X has n points and it's d-dimensional, such that any embedding of that hard set into m-dimensional Euclidean space must have distortion, which has distortion 1 plus epsilon, must have dimension at least 1 over epsilon squared log n times some constant factor. You might wonder about this, like why have this weird condition on epsilon that can't be, well, okay, so epsilon cannot be too small. That makes sense because what if, okay, anyway, why this condition at all? And the reason to have that condition is there are always two trivial solutions. One is you can always take your embedding to be the identity map, okay? That would embed into dimension d. And you can always embed into dimension n or n minus 1 because if you have n points span and n points live in an n-dimensional subspace, namely the subspace that they span. In fact, if you only care about preserving distances, you can translate all the points. Translation does not change distances, pairwise distances. Translate the points such that one of the points is at the origin. And now you only have n minus 1 dimensional subspace that the points live in, which means you can embed into dimension n minus 1 and not change the distances at all. So you can always achieve basically dimension, which is the min of d and n. So if 1 over epsilon squared is bigger than the min of d and n, you would prefer to just use one of these solutions instead, which means you don't really care about epsilon that's too small. Okay, so that's why that condition is sensible, right? Which is what I wrote here. So you can only hope that JL is optimal when the JL bound is less than the min of n and d. So the theorem assumption there is basically saying we only care about this lower bound when the JL bound is much less than this. Okay, so great. Now, how do you actually prove the lower bound? It's going to be an encoding argument. Ultimately, it's the pigeonhole principle. What do I mean by an encoding argument? I don't actually know, even today, I don't know a specific point set. So what does this say, right? The theorem said there exists, right? There exists a point set which is hard, which you can't do better than JL. If you ask me today, what is that point set? I don't know. I still don't know. I mean, that's an open question. Come up with an explicit point set that's actually hard. Describe it to me. I have no idea. But I can prove that it exists, okay? And it's going to be via the pigeonhole principle. And how does that work? So roughly, the sketch of the proof looks like this. I'm going to define not just one point set, but a collection, script X, of many point sets. So every element of script X is a subset of points in d-dimensional space that has size n. And script X is going to be designed such that it has the following property. If it's true that every point set in script X can be embedded in much less than the JL bound, can be embedded in dimension 10 to the minus 10 times the JL bound. If that's true, then I will be able to use that fact to prove that there is an encoding of elements of script X into less than log of script X bits. In other words, there's an injection from script X into bit strings of length t, where t is less than log of script X. And you cannot have an injection from a big set into a smaller set, so this is a contradiction. Okay? So that's how the argument's going to go. Okay. So now what are the specifics of the argument? For now, I'm going to assume that D is some very specific thing, but that can be removed later. So the first observation is that if you preserve Euclidean distances, you also preserve dot products. Why is that? So let's just say that I have two vectors x and y that have unit norm. And the claim is that if it's true that the embedding, now f could be a nonlinear embedding. It doesn't have to be linear, but f is some embedding. If it's true that f of x has roughly the same norm as x, f of y has roughly the same norm as y, and f of x minus f of y has roughly the same norm as x minus y, I claim that the dot product is the same up to an additive O of epsilon. And I guess I didn't write down the proof of this, but the reason this is true is that I can use, I guess, what is that called? Is it parallelogram rule? So if I look at x minus y L2 norm squared, what is that? It's x minus y dotted with x minus y, which is the norm of x squared plus the norm of y squared minus twice the dot product. So that's where the dot products come in. So x minus y L2 norm squared is norm squared of x plus norm squared of y minus twice the dot product. I can do the same thing for the norm of f of x minus f of y. The norm of f of x minus f of y is norm of f of x squared plus norm of f of y squared minus twice the dot product of f of x and f of y. And if these two distances are roughly the same, I can subtract the two equations and basically get the dot products have to be roughly the same. Okay, so I didn't write it down carefully, but it's just basically using the parallelogram rule to say that preserving norms implies you preserve dot products. Okay. So now how am I going to use this to design script X? So here's the lower bound idea. I'm going to pick a parameter k, which is an integer. And I'm going to pick k to be like, let's say, the ceiling of this, 1 over 100 epsilon squared. And for a subset S of coordinates where S has size k, I'm going to define y sub s as the indicator vector of the set S, normalized to have unit Euclidean norm. So y sub s has a 1 in the jth coordinate for all j and s. And then I divide by root k, so it has unit norm, Euclidean norm. Okay. And now notice that if I look at the ith standard basis vector dotted with ys, it's 0 if I is not an s. And if I is an s, it's square root 1 over k, which is 10 epsilon. Okay? In other words, taking dot products of ys with standard basis vectors reveals information to me about s. It tells me whether that element is an s or not an s. It's like I learned a bit of information about s. You can think, okay. I like to think about this whole proof as like reasoning about information and encoding information. So dot products encode information in some way. Okay. And now, so this is the actual dot product. But remember, like, we're doing embeddings, right? So I might not, once I see the embedded vectors, I don't know the actual dot product. I know the dot product up to some additive error. So the dot product of the embedded vectors will be the actual dot product up to some error. But that's okay, because it'll be like 10 epsilon plus or minus epsilon, or 0 plus or minus epsilon. But those two intervals are disjoint. So I still know the information. I can still discern whether I is an S or not based on the dot product between f of x, between f of ei and f of ys. Okay. And now script x is going to be the set of all ordered tuples of points. I slightly lied earlier. I said that script x was a collection of sets of points. Here it's like tuples of points that might have repetition. It doesn't really matter, okay? The lower bound still works. So script x is the set of all ordered tuples of points, possibly with repetition, that have the following form. It's always 0, followed by the standard basis vectors in order, followed by y sub s1, y sub s2, et cetera, where these s's are arbitrary. They're arbitrary subsets of size k. Okay? So the si's are k element subsets of 1 to d. So what's the size of script x? Well, these first d plus 1 vectors are fixed. Only these vectors are allowed to vary. So the size of script x is d choose k raised to the power n minus d minus 1. Because d choose k because that's how many s's there are, and n minus d minus 1 because that's how many I have to pick. Okay. Thus, any encoding of x as a bit string must use at least the logarithm of this many bits, which is roughly n times k times log d over k bits. Okay. And what I'll show you now is that any 1 plus epsilon distortion embedding, so if it's true that for every capital X in script x, there's a low distortion embedding into m dimensions, I'm going to show you that that implies that for any capital X, I can encode it into nm bits. Therefore, nm must be at least nk log d over k. The n's cancel, and m must therefore be at least k log d over k, which is, if you look at what k is, and remember I chose d to be something very specific. I said d is something very specific. Then I get the lower bound I want. I get the lower bound of 1 epsilon squared log n. So the name of the game at this point is to show why is it true that if every capital X can be embedded into m dimensions with low distortion, that implies the existence of this injection, this encoding into bit strings of a few bits. That's the name of the game. So let's think about this together. Here's my first idea for an encoding. Well, I can just say, okay, capital X is 0 up to ed, followed by ys1 up to ysn minus d minus 1, right? So here's what I'll do. F of 0 is what? F of 0 is an m-dimensional vector. It's m numbers, right? It's an m-dimensional vector. So it's m numbers. That's m numbers. That's m numbers. Each of these is m numbers. They're n vectors. In total, it's n times m numbers. So that's my encoding. My encoding is I'll just write down these n times m numbers. So I now have my encoding of length n times m. So I'm done, right? I just proved that JL is optimal. Okay, so what's wrong with that proof? Any takers? Why that's wrong? Right, the name of the game was, show that there's an injection into bit strings with few bits, bit strings that are short, in particular n times m bits. We know that any injection into bit strings must have bit strings of length at least nk log d over k. Therefore, nm is at least nk log d over k, and we're done, right? So I just showed you that there's an encoding into nm numbers. So there's nothing left to do, right? Oh, yeah. Yeah, well, I mean, they do, right? Because f is an embedding into m dimensions. So that's m numbers right there, m numbers. I just concatenate all the numbers. They're nm numbers. But I don't need to do better. I just needed to prove to you that there is an injection. There is an encoding. So here it is. This is the encoding. I just at the end of the day need an encoding of length nm. So there are n vectors here that are on the slide. Each one is m numbers, so nm. Okay, right. So I mean, okay, so I guess no one. So I'll just tell you what's wrong. What's wrong is I need an encoding into nm bits. These are nm real numbers. Okay, so that's the problem. Okay, that's it. Okay, so this doesn't work. Okay. Remember, at the end of the day, I'm trying to do a pigeonhole, right? So I need to basically count. How many bit strings are there with nm bits? 2 to the nm. How many bit strings are there of length, whatever, 2 to the nk log d over k. I mean, you can't do that counting when these are real numbers, right? So that's, I need to actually be nm bits, not nm numbers, not nm real numbers. Yeah, so the problem is that we're trying to violate the pigeonhole principle, so we need to actually have bits. Okay, but okay, so that seems easy enough to fix, right? You can say, well, okay, if the problem is that these are real numbers, why don't I just like round them to finite precision? Just discretize them. And now that they're discretized, I can actually write bits down. Okay, so what's, anyone think anything's wrong with that? Yeah. Okay, so yeah, and so, okay, so actually, the thing is, this actually does give you something, and it's not bad, but it's just not like exactly the right answer. So the point is, if you ask yourself, well, how much precision do I need? Remember, what is the goal at the end of the day? The goal, I need to encode information. The information I care about is the dot products. The dot product is either 10 epsilon or 0, right? As long as I don't mess up the dot product by more than an additive epsilon, I can still discern which case I'm in. Or even an additive 4 epsilon, I can still discern which case I'm in. So I just need to make sure that I don't change the dot product by more than an additive epsilon. And you can show that as long as you round the entry, so you can say, let me round the entries of fx to integer multiples of gamma, where gamma is like my precision parameter. You can show that as long as gamma is epsilon over root m, then you will actually preserve the dot products up to additive epsilon, which means that the number of bits you need per number is log 1 over gamma bits. Okay, so there are nm numbers. Each one you need log 1 over gamma bits. So the total number of bits you need is nm log m over epsilon. And if you run what that actually gives you, it gives you that m is at least omega this. It's a little weird looking because m depends on itself. But you can solve the equation, and you basically will get, if you solve the equation for m, you'll get that this is what you'll end up getting. Okay, so 1 over epsilon squared log n over log n plus log 1 over epsilon, which is like really close to 1 over epsilon squared log n, but it's not quite there. Okay, so then you can look at this and say, well, how can I do a little bit better than this? So are people familiar with the concept of like an epsilon net? Who's heard of an epsilon net? Okay, so, right, an epsilon net is like with respect to some norm, right? It's like you want like a discretization of your space, so that you can like round any point to someone in the net that is close to you under that norm. And you want this discretization to be like to have as few points as possible. Right? You want to minimize, let's say you want a small net as possible. So if you think about what we actually did in this fix attempt, we rounded every vector in an L infinity net. Right? We said that every entry we're gonna snap it to the grid to some integer multiple of gamma. So that's an L infinity net with L infinity error gamma. And why did we do that? We did that because we wanted to preserve dot products. But that's a little bit unnatural. Like, why am I rounding in an L infinity norm if I want to preserve dot products? If I want to preserve dot products, as we saw from the parallelogram rule, dot products are very closely related to Euclidean norms. So if I'm trying to preserve dot products, maybe instead I should take an L2 net, and I should round to the closest point in an L2 net. So you can do that, and if you do that, you're going to get rid of the log n. Basically, you can show that the epsilon net in L2 has size 1 over epsilon to the m. So if you take the log, so specifying the name of a point in the net takes log of that number of bits, which is m log 1 over epsilon bits. So you have n vectors here. Each vector is being snapped to the closest point in an L2 net. So each of these n vectors, you're taking m log 1 over epsilon bits to specify the rounded vector. So overall, it's nm log 1 over epsilon bits. So the lower bound you get at the end of the day is 1 epsilon squared log n over log 1 over epsilon, which is actually the same exact lower bound as Noga Alone's paper from 2003, I think it was, except he had a completely different argument. But our goal is not to match Noga Alone 20 years later. Our goal is to like finally get the right answer. So, okay. So I think I'm almost done wrapping up this proof. We'll take our break very soon. So we're going to do one last thing to improve this. Okay. Yeah. So as I mentioned, same lower bound as Noga, just to be a different argument. So the very last thing to improve it is the following. So remember now, what I really wanted to know was EI dotted with YS for every S and for every I, because that gave me the information about which I is in which S or not, right? And then I could decode everything. And then I said, well, those dot products were either 0 or 10 epsilon. So if I have error epsilon in my dot products, I can still tell the difference. So knowing the dot product between f of EI and f of YS is still enough information, okay? And in fact, I don't even need to know the actual dot products between f of EI and f of YS. It's enough to round f of EI in an L2 net and round f of YS in an L2 net, and then know the dot products of those. And the tilde for me just means rounding in the L2 net. So as long as I know all of these dot products for each I and j, that's enough information to know all the sets S and basically decode and figure out what X was. So let's write down the information we need to know in matrix form. I'm going to define a matrix A whose rows are the tilde FEIs transposed. And then what I'm saying is for any Sj, for any subset of coordinates Sj, if I look at the vector f of y Sj tilde, and I take the matrix A times that vector, then at the end of the day, that gives me this Vj, this vector, which is all the dot products. And as long as I know all the Vjs, I'm happy, right? Okay. In fact, I don't even need to know Vj precisely. It's enough to know Vj tilde, which is a rounding of the Vj in L infinity net. Because as long as I know each entry of Vj up to additive error epsilon, now I've added epsilon error 3 times. So now my errors are 3 epsilon. But 0 plus or minus 3 epsilon and 10 plus or minus 3 epsilon are still disjoint intervals. So I can still tell what's what. So in fact, it suffices to know all the Vjs rounded in L infinity net. And now this is the last slide in terms of this proof. Almost last. Okay, this is the last slide that matters. Okay. So let's just write down everything we know. This matrix A is a D by M matrix. F tilde YSJ is an m-dimensional vector, and these Vjs are in Rd. Okay. Let capital E denote a certain subspace. Namely, it's the subspace of Rd, which is spanned by the columns of A. A only has m columns, so it's an m-dimensional subspace of Rd, or at most m-dimensional subspace of Rd. Now I'll define a certain convex body K. K is the L infinity ball in d dimensions of radius 13 epsilon, intersected with that subspace, which is the column space of A. Why did I define K this way? Because K captures what I know about the Vjs. All the Vjs are in K, right? All the entries of Vj are at most 13 epsilon. And they're definitely all in the column space of A because they're A times some vector. Who here, I guess, is familiar with like the relationship between symmetric convex bodies and norms? Right, so, okay. So you're familiar with norms, L1 norm, L2 norm, L infinity norm, whatever. Norms and symmetric convex bodies about the origin are basically the same thing, right? Why? If I have a norm, let's say I have the L2 norm, I can say what's the unit ball of the L2 norm? It's a sphere, right? Or what's the unit ball of the L infinity norm? It's a cube. So norms give me unit balls. And then similarly, if I have a symmetric convex body, it defines a norm. What's the norm? The norm is just, the norm of a vector is simply what do I need to scale the vector by to get on the boundary of the unit ball of that one? Oh.
Yeah, there's some noise.
Yeah, is it me? Do you know? Okay, well, it's gone now. I think it's gone. It's okay. I don't know what that was. But yeah, so if you have a norm, you have a unit ball, you have a symmetric convex body, which is the unit ball. If you have a body, if you have a symmetric convex body, you can just define the norm. You can say the norm is such that this body is the unit ball. Whatever norm makes this be the unit ball, that's my norm. Okay? So now that we have a symmetric convex body K, I can define the K norm. Right? It's whatever I need to scale vectors by to get on the body. And this is just a general fact about norms. If you take the unit ball of a norm and try to come up with a net of that body in its own norm. So I take this K norm and I try to come up with a net of the K norm in the K norm. I take the net of the unit ball of the K norm in the K norm. An alpha net. An alpha net has size 1 over alpha to the dimension of the body. So a 1 over 13 net has size 13 to the dimension of the body, which is m. Okay, so good. And now I'll define Vj tilde as the closest point in this net to Vj. And because of how I define the body and also the fact that I took a 1/13th net, it implies that Vj minus Vj tilde has L infinity norm less than epsilon. Okay? And how many bits does it take to specify Vj tilde? Log the size of the net, which is O of m bits. So remember, there are basically there are like n minus d minus 1 different Vj tildes. Each one takes O of m bits to specify. So in total, to write down all the Vj tildes takes nm bits. So I'm done now, right? I've taken nm bits to actually specify all the Vj tildes. Okay, except I lied to you slightly. I didn't lie. I lied at the very end when I said I'm done. Nothing else was a lie. But I'm not actually done. And the proof that I'm not done is that there's still space right here on the slide. So there's one thing that I kind of swept under the rug. I did like a magic trick where I moved fast and hoped that you would miss something. So what did I not say that's actually important? Okay, so let's just think again about what this proof is doing. It's an encoding argument, right? Think about it like there's an encoder and a decoder. The encoder has a capital X, which is a point set, and they're trying to write down a bit string to later help the decoder decode and figure out what capital X was. Okay, so the encoder got capital X. It knows that for that capital X, there is a good embedding, F. So it knows the embedding. It knows the embedding because it knows capital X. It computes the embedding on all the EIs as well as 0, as well as all the YSJs. It then forms this matrix A. It knows the matrix because it knows all the it knows all the FX tildes. Now that it knows the matrix, it knows the body. And then it can then just round all the VJs in the body and then spit out like which net element each thing rounds to. And then it writes down, okay, this is V1 tilde, this is V2 tilde, this is V3 tilde. In particular, what does it mean that it writes down V1 tilde? It's like V1 tilde is the 27th element of the net. So it writes down the ID in some ordering of the points of the net. So now you're the decoder. You see this being written down. Like, what do you see? You see, okay, V1 tilde is the 27th element of the net. V2 tilde is the second element of the net. And now you need to decode. What are you missing? You're missing some information that you really need to be able to decode. What are you missing? And just to be clear, like, the reason I'm talking about in this encoding decoding language is I want to prove that it's an injection. The easiest way to prove that it's an injection is to prove that you can invert it, right? That looks like a unique way to invert it. Yeah. Yeah, you need the space E, exactly. So the problem is the decoder doesn't know what K is. They don't know what the body is because the body depends on E. E depends on A. A depends on F. Well, A depends on F as well as, yeah, it depends on F, right? It doesn't depend on the YSJs, but it does depend on F. But F depends on capital X. Each capital X has its own F. But the decoder doesn't know capital X. So it doesn't know F. So it doesn't know what A is. Okay. So the last thing I'll do is I'll tell the decoder what E is. Hi, Piotr, thanks. I've lost my connection. Okay. Anyway, so I'll just tell it A, which means I'll just write down this matrix. So remember, each one of these things is an element of an L2 net. So it takes m log 1 over epsilon bits. There are d of them. Oops. There are d of them. So in total, it's dm log 1 over epsilon bits, which is nm bits to write this down. So in total, the whole thing is nm bits. So now I'm really done. What about when d is not exactly equal to n over log 1 over epsilon? So that's actually quite easy to handle. So what you can do is say, well, suppose, okay, so now we know that there exists a hard point set in d prime dimensions where d prime is n over log 1 over epsilon, right? That's what we just proved. We proved that when d is the specific thing, there is a hard point set. If you want to prove that there exists a hard point set for a different dimension, well, if the different dimension is bigger than d prime, just take the hard point set in dimension d prime and zero pad it to all have dimension d. That's going to be a hard point set too, because it's basically the same point set. You haven't changed anything. If d is less than d prime, then take the hard point set for dimension d prime and apply JL to it. Apply the JL upper bound to it. And the point is, if x is a hard point set in dimension d prime, then f of x must be a hard point set in this lower dimension. Otherwise, x wouldn't be hard. So otherwise, you could compose the embeddings and have a lower dimensional. You would have a low dimension embedding for the original hard point set, which you know doesn't exist because you proved it doesn't exist. Okay, so I think I will pause here for 10 minutes and let people stretch and stuff, and then we'll resume at, let's say we'll resume at when that clock says 11:35.